All right, guys. Good day. This small lecture or information based on the last topic on vibrations, waves, and sound. This will help you answer questions on chapter 14, sound assignment. I will go over some of this quickly because some of those are just applying certain formulas, like here, just do distance over time or velocity times time to find distances due to sound waves. In some other problems, you need certain concepts like fundamental frequency, sound waves in tubes, and the most, interesting and sometimes a bit confusing topic, the Doppler effect for sound. So in the previous video, when I was going over the examples, I already talked about waves. So there are problems based on waves in the previous assignment and on this chapter 14. In general, remember that we have two types of waves, the transverse waves and longitudinal waves. A transverse wave is like the one that you are seeing in front of you, and is the one that we use to describe light or mechanical waves on a rope. You see, you have the amplitude going up and down, and the velocity moving from left to right. The perturbation per se is going up and down, but is moving along the wave from left to right. The wave can be characterized by the amplitude, the wavelength, the speed, and also the frequency and period. Additionally, we know that a wave carries energy, right? So that's why we know electromagnetic waves in vacuum, they are a source of energy, basically light. For longitudinal waves, the displacement is on the direction of the motion of the wave. And we're going to look at that for sound. We're going to be looking at that in springs, right? That's when you have longitudinal waves. Now, for transverse waves, for example, for water waves or light, you will have them illustrated like this, where the wavelength, like I showed you in a previous class, is the distance between two peaks, measuring meters with a variable lambda, and the speed is just v. So the equation that you should always remember is that the speed of the wave is that the speed of the wave is equal to lambda times frequency. Very important. And this comes from the fact that lambda is the distance traveled by the wave in one period. So it's basically v times the period t. But we know that t is the inverse of f. So if you plug this in here, then you have lambda times frequency equals to v. That's why. Okay? Remember again, t is period, is the distance traveled by a wave in a given period. Sorry, period is the time that a wave travels, is the time, it measures the time for a given wavelength. I always get that confused for some reason. I don't know. Sorry about that glitch, guys. Period is time in seconds. So a wavelength is v times the period. Okay? And it's probably easy if you remember your circular motion. One revolution is the distance traveled by a mass in one period. Now, what makes it easy in circular motion is that the circumference is just 2 pi r. All right, so we kind of do the same for a wave. It's very easy. It's just that sometimes the terms can be a bit, period, frequency. So just be careful with that, all right? Uh, Period is a measurement of time in seconds. Wavelength is in meters. Velocity or speed is in meters per second. And here it is, right? All the parameters for our wave. You have the speed, the distance, in this case lambda, wavelength, time, period, frequency, the inverse of the period. And on a string, we can add a couple more of parameters. You have the tension on the string and the composition, which is basically given by the mass and the length. If you have the mass and the length of the string, you can get the linear density. So there is an equation that you're going to see where we say that V is equal to the square root of tension divided by mu. And what's that mu? It's not coefficient of friction. It's M over L. That's the linear density of the string. Okay? Normally, you apply certain force to create some tension, like in a guitar, or just to produce waves, mechanical waves. That would be your tension or your force. The mu is the ratio between the mass of the string and the total length of the string. Very important because eventually we're going to use that equation for fundamental frequencies and waves in a pipe. So there it is, the definition of mu. All right. And here's the formula. Here they use F instead of T. F is basically a force. T is also a force, right? So the speed of the wave increases as you increase the force and decreases as the mass. Makes sense, right? The more mass, the less speed. It's harder to make it vibrate if you think about it. You can also have reflection of waves. So when a wave reaches the end of the string, it will be reflected. If the end is fixed, then it will be inverted once it's reflected, like you are seeing in the picture. Now, how do we characterize waves? This is also an equation that I gave you in class, like in a previous video. But we normally say that the function wave depends on two variables, x and time, where this could be a sine or cosine of kx minus omega t. What's that k? We don't have a spring in a wave, but we have the wave number, 2 pi over lambda. And what's the w? Well, the w is 2 pi over the frequency. So we have these parameters, the wave number and the angular frequency. Right? Your variables are now position and time. Okay? This is a fundamental equation for a wave. Let's take a look at what we have in the slides. There it is. So instead of using k, they use 2 pi over lambda. All right. And here they just use the function as a function of x. If you include time, you have the overall equation kx minus wt. Here it is. All right. You can use cosine, you can use sine, it depends. If you want to use sine, you have to add an extra parameter, which is the phase. Normally, that phase will be, for example, a sine of kx minus omega t. This could be plus pi over 2. There. If you add or subtract pi over 2, the function changes from sine to cosine. So that's the phase. And it makes sense if you think about it, right? If you move this pi and a half to the right, you will have this. And that's your sine function then. Okay? So one of the main topics of this chapter is sound waves. Half of the problems in the assignment are about sound. You have them as longitudinal waves, similar to the waves on a slinky, like you have in front of you. You have that the wave is a series of compressions and stretches. So like this, kind of like a simple harmonic motion, right? In the case of a sound wave, the density and pressure of air or any medium where the sound wave is moving are the quantities that are oscillating. So you see density and pressure. The speed of sound depends on the medium, right? In solids, it's very quick, like you see aluminum, steel. In water, it's kind of quick, not as much, and then it's slowest in air, 343 at standard room temperatures, right? All of those are in meters per second, by the way. Sound waves can have any frequency that ranges between 20 and 20,000 hertz when the human can hear it. So that's the range of frequencies. Any sound frequency greater than 20,000 are ultrasonic. Any sound frequency below 20 hertz are infrasonic. All right. Now remember, some animals can detect beyond the human capability. All right. For example, elephants, whales, right? They communicate by infrasonic waves, right? Just like in light, there are certain birds that can observe ultraviolet. We can't, but certain animals can. That's called evolution, right? And adaptability. Now, I told you that a wave carries energy. If energy is going through a region in certain time, we can determine the amount of power. And if you have power, for example, when you have light striking a solar panel, light is a wave. That solar panel is receiving power, but also intensity, which depends on the surface area of the panel. So there is an equation that gives you the intensity of a wave. The intensity is basically this, where energy over time is power. So power over area, watts per meter square. Those are the units for intensity, sound intensity. And you can find it here, right? And a good example will be, for example, a source of sound. It can be an alarm that is beeping, right? In electromagnetic waves, we normally use antennas. Antennas emit signals in every direction in space. Now, let's use sound for this, okay? So if you have a sound source, it can be again an alarm. You can draw the sound waves like this. Right? Because they go in every direction, they enclose an spherical region with certain radius r. It's a sphere because we're looking at 3 dimensions. So the area, in this case, the area of the region is the area of the sphere, which is 4 pi r squared. So you can say that the intensity for that given source as a function of distance is the power, which normally you can find, divided by the area, which depends on radius, 4 pi r squared. A very useful, not formula, but definition, all right, of what power and intensity are. And they also have it here. Intensity with a distance from a point source. An example of this can be bats. Bats can use this decrease in sound intensity to locate small objects in the dark. Right? Remember that they actually can hunt insects inside caves. They can use this. Right? And there's a problem in the assignment where you have a bat trying to reach an insect using echoes. I will go over that problem in the next video, but it's basically sound waves and a little bit of the Doppler effect. Now, when you listen a variety of sounds, we have a scale. We use the decibel scale. The decibel scale is defined as what you see right in front of you. It's basically a logarithmic scale to define wave intensities. So this intensity level beta is equal to 10 decibels log of I over I naught, where I naught is the value of 10 to the negative 12 watts per meter squared. Is the lowest sound intensity you can hear. So it's a scale, right? And if you want to find the amount of decibels, you need to know the intensity of a given wave. So you will see when you do the problems how this works. But there's a table here for the values of beta, right? For example, the amount of decibels of a subway is about 100. So you can use that, and let's actually do an example, right? If you have the amount of decibels, let's see the intensity of a subway. Yeah. So if we say that the amount of decibels are 100 decibels, 100 is your beta, which is defined as 10 decibels log of I over I naught, which we know is 10 to the negative 12. Parenthesis. This cancels, and you have 10 there. Log means base 10. So 10 to the 10, all right, that's quite a number. That's equal to the intensity of subway divided by 10 to the negative 12. If you multiply here, you get that the intensity of the subway train is about 10 to the negative 2 watts per meter squared. So not a lot, but still loud enough to hear it. All right, so that's a good example there. A jet taking off, obviously gonna be more. You start having pain at 120. Interesting. Heavy traffic, 70. So when you guys complain about the city being so loud, keep in mind that in terms of decibels, it's probably not really a lot. It is high, but not really. No. A conversation, 60, in a classroom, 50. So not bad, right? And you can use these numbers to find the intensity level of a conversation, for example, like I just showed you on the screen using this equation. Okay, so now let's talk a little bit about the Doppler effect. You see, normally when I teach the Doppler effect, I do it in astronomy. We talk about, for example, galaxies receding. There is, I believe, let me see here. Yeah, there is a discussion board about Doppler effect and redshift of galaxies that you guys have already been responding. Basically, if a source is moving towards, or if the galaxy is moving away from us, the wavelength and frequency that we are going to measure from the light are not the ones expected. We normally use hydrogen emission for that. So hydrogen emission have fixed positions of their emission spectra. We know the wavelength for hydrogen. But when we analyze the hydrogen from receding galaxies, we see that they are redshifted, meaning that the wavelength has been stretched by the expansion of the universe, right? By the motion of galaxies receding from one another. Now, in the case of sound, the best example will be, say, a police car or an ambulance. If you are heading towards a police car whose alarm is beeping, the frequency or the intensity of that sound is going to increase, which correlates with the frequency. The closer you are to the source, the more frequency. If you are going away from the source, the frequency will decrease. So one advantage of sound for the Doppler effect is that you don't have to worry about the wavelength. Redshift comes from the idea of wavelength stretching. And then blue shift if the wavelengths are compressing. For the Doppler effect, we only care about frequency. Either the frequency increases or decreases. And the logic is as follows. If you are going towards the source, the frequency will go up. So the measured frequency by yourself is going to be greater than the frequency emitted by the sound. And I'm going to show you with an example after this from the book. If you are going away from the source, the frequency will decrease. All right? And you have the equation here. If the observer is moving towards the source, the new frequency will increase. So do you see this fraction here? This is 1 plus. What's u? The speed of the person going towards the source. If you are moving away, it will be minus. So the frequency will decrease. The f prime will be less than f. So here is the intensity level again. And here is the Doppler effect. Now with a moving source. All right? If the source now is moving and the observer is stationary, now that u is the source speed. Again, if the source is coming towards you, the frequency will increase. If the source is going away from you, then the frequency will decrease. So here is the equation for the Doppler effect with a moving source, right? If the source is moving towards you, it will be 1 minus u over v. If the source is moving away from you, 1 plus. Remember, the larger the denominator, the lower will be the answer, right? Because the larger the denominator, the lower is this fraction. So then the new frequency will be less than the actual frequency. This will make more sense with examples. If you combine both, a moving observer and a moving source, you have that equation there. So let's see. Let's look at this, and let's see a problem on the same gauge. Okay. Let's practice another. A baseball hits a car, breaking its window and triggering the alarm, which sounds at that given frequency, 1210 Hertz. What frequency is heard by a boy on a bicycle riding away from the car? So the person is moving away from the source. If you look at this, the source is the alarm, which is not moving. So this is 0, right? Um, guys, I'm gonna show you something that you have to be careful though. So if you rearrange this equation, f prime is 1 plus minus, or no, I don't want to use that. Let's erase this. So f prime is v plus minus u observer over v minus plus u of the source, all multiplied by f. You know why I'm doing that? Because if the source is stationary, that's 0. So you only have v, where v will be basically the speed of sound. If an alarm is beeping, it's reaching towards you because that's the speed of sound. V sound. U of the observer, plus or minus, right? What did I just say? The boy in the problem is riding away. So the frequency is going to be less than the actual frequency. So the boy is moving away at 8 meters per second, and that's the frequency actual. So using the Doppler effect, the new frequency is the old frequency multiplied by 343. Instead of positive will be, because it's going away, minus 8 over V, which is 343. All right. Now let's use a calculator. 3 minus 8 divided by 343. Ay. $1,181. So it will be less than the actual frequency. So you see, that's how you solve problems with Doppler effect. First, you're gonna rely on this equation. This is the equation you wanna use. If the source is not moving, this is just 0. If the source is moving, then you have to be careful, right? Because remember, if the source is moving towards the person, it will be V minus US. Because if you're moving towards the person, the frequency is going to increase. All right. If you're moving away from the source, it will be V plus. Or if the source is moving away, V plus US. Okay. I will do a couple more problems on Doppler effect in the next video so you guys can see how really this works. But here you have a good example. Then I want to go into, you don't have to worry about superposition, interference. That is important, but it's more like what happens with sound waves. They superimpose, there is interference, and this makes a lot of sense once we talk about interference and diffraction of electromagnetic waves, which is basically what is used for the Young double slit experiment and every form of diffraction. Light can go through a slit and you have a series of bright and dark spots. We call them fringes. Why is that? Because light acts like a transverse wave. And transverse waves, they can interfere constructively or destructively. It depends. So here you have it. Constructive interference or destructive interference. That's the idea behind these slides. The last thing I want to talk about is sound waves in a pipe and standing waves. So standing waves is when you have two fixed points, like a guitar, and then you create a perturbation. You have a wave that can be formed like you have in front of you. That, if you think about it, is half a wavelength. So half a wavelength is the length of this. So if half a wavelength is the length of the string, then the wavelength is twice the length of the string. Here is where we define fundamental frequencies for standing waves, which is here. Standing waves on the string. The frequency will be 2L, which is the wavelength, times the frequency, that's the speed. You can find the frequency by just dividing V over lambda. Lambda is 2L, so you have the equation there. Now, that's for one harmonic. If you have two or three harmonics, you have the general equation n over 2L times V, where n is the number of harmonics. The fundamental frequency is when n equals to 1. Now, why are we doing that? Well, because we have standing waves like that. You have the nodes, the antinodes. Antinodes are these, by the way. Nodes are these points where the string doesn't move. All right. Points on the string which never move are called nodes. Yeah, basically. The antinodes are the ones that are going up and down. Again, the best example of this will be a guitar. In order for different strings to have different fundamental frequencies, they must differ in length or linear density. Why linear density? Because the equation for frequency depends on V, and V is the square root of tension divided by mu. Mu is the linear density, which is a difference on mass and length. So yes, you can either vary the length or the mass or both. That will give you a different fundamental frequency. That's how a guitar works. In a piano, the strings vary in both length and density. This gives the soundbox of a grand piano its characteristic shape. Well, there you have it. If you were wondering about that, there you have it, right? So musical instruments in general are designed so they have a variation in tension, and between the different strings is small. So the variation in tension is small. Now, you can also have sound waves in tubes. You have here. And I'm going to show you this actually for that. I had it here. There it is. That's what I wanted to show you. So when you have tubes closed at one end, you start having the wavelength reflecting like this. Now, if you think about it, this is a quarter of a wavelength, not half, like in the standing wave example. So for a tube that is closed at one end, like for example here, a quarter of a wave for the first harmonic will give you that the length of the tube, 4 times the length of the tube will be the wavelength. Because, again, the length of the tube is a quarter of the wavelength. So the wavelength is 4L. That will give you the following equation. Frequency equals to N over 4L times V. This is the fundamental frequency for a tube closed at one end. Now, be careful though, because you're probably wondering, what about 2? What about 4? That will make it. That's why for a tube that is closed at one end, the values of N are only between, well, only odd numbers. So 1, 3, 5, 7, etc., etc., etc. You don't use the even numbers. Those actually are only used for standing waves or if the tube is open at both ends. If the tube is open at both ends, the first harmonic will be that lambda equals to 12. For the second harmonic, lambda equals to L. You think about it, this is a whole lambda. Okay, I might have to use